Plutonium-238 is a radioactive isotope of plutonium that has a half-life of 87.7 years. Plutonium-238 is a very powerful alpha emitter and, unlike other isotopes of plutonium, it does not emit significant amounts of other, more penetrating and thus more problematic radiation. This makes the plutonium-238 isotope suitable for usage in radioisotope thermoelectric generators and radioisotope heater units. 1 gram of plutonium-238 generates approximately 0.5 watts of thermal power. History: Plutonium-238 was the first isotope of plutonium to be discovered. It was synthesized by Glenn Seaborg and Associates in 1941 by bombarding uranium-238 with deuteriums, creating neptunium-238, which then decays to form plutonium-238. Plutonium-238 decays to uranium-234 and then further along the radium series to lead-206. Production: reactor-grade plutonium from spent nuclear fuel contains various isotopes of plutonium. Pu-238 makes up only 1 or 2%, but it may be responsible for much of the short-term decay heat because of its short half-life relative to other plutonium isotopes. Reactor-grade plutonium is not useful for producing Pu-238 for RTGs because difficult isotopic separation would be needed. Pure plutonium-238 is prepared by neutron irradiation of neptunium-237. In both cases, the targets are subjected to a chemical treatment, including dissolution in nitric acid to extract the plutonium-238. A 100 kg sample of light water reactor fuel that has been irradiated for 3 years contains only about 700 grams of neptunium-237, and the neptunium must be extracted selectively. Significant amounts of pure Pu-238 could also be produced in a thorium fuel cycle. United States supply: the United States stopped producing bulk plutonium-238 in 1988. Since 1993, all of the plutonium-238 used in American spacecraft has been purchased from Russia. In total, 16.5 kilograms have been purchased, but Russia is no longer producing plutonium-238 and their own supply is reportedly running low. The United States Pu-238 inventory supports both NASA and other national security applications. The Department of Energy maintains separate inventory accounts for the two categories. As of March 2015, a total of 35 kilograms of Pu-238 was available for civil space uses. Out of the 35 kilograms inventory, 17 kilograms remains in good enough condition to meet NASA specifications for power delivery. It is this pool of Pu-238 that will be used to in a multi-mission radioisotope thermoelectric generator for the 2020 Mars rover mission and 2 additional MMRTGs for a notional 2024 NASA mission. 21 kilograms will remain after that, with approximately 4 kilograms just barely meeting the NASA specification. This 21 kilograms can be brought up to NASA specifications if it is blended with a smaller amount of newly produced Pu-238 having a higher energy density. To restart production, a sustained year-to-year funding would maintain the infrastructure and knowledge base in order to avoid significant recapture costs. Approximately $50 million per year, formerly funded by Department of Energy, was transitioned to a full cost recovery model as part of the FY 2014 federal budget. NASA has also provided additional funding to refurbish critical equipment at LANL. Department of Energy manages the operation of its nuclear facilities in order to ensure nuclear safety, security, to meet mission needs, and to obtain synergies with programs A project to re-establish Pu-238 production capability has a total estimated cost range of $85–$125 million over 9 years. But actual project costs are likely to increase since available funding has not supported the planned pace, thus drawing out the schedule. After production has been restarted, it is predicted that it would take at least 5 years to get enough for a single spacecraft mission. The Advanced Test Reactor at the Idaho National Laboratory and the High-Flux Isotope Reactor at the Oak Ridge National Laboratory were both seen as potential producers. In February 2013, it was reported that a small amount of plutonium-238 was successfully produced by Oak Ridge's high-flux isotope reactor. This was the first time the United States had produced 238 Pu since production ended in the late 1980s. On December 22, 2015, the Oak Ridge National Laboratory reported that its researchers had successfully produced 50 grams of plutonium-238. After an analysis of this sample, production of 300 to 400 grams of the material per year is planned to begin, and then, through automation and scale-up processes, production will increase to an average of 1.5 kilograms per year. Applications. The main application of Pu-238 is as the heat source in radioisotope thermoelectric generators. RTG technology was first developed by Los Alamos National Laboratory during the 1960s and 1970s to provide radioisotope thermoelectric generator power for cardiac pacemakers. Of the 250 plutonium-powered pacemakers Medtronic manufactured, 22 were still in service more than 25 years later, a feat that no battery-powered pacemaker could achieve. This same RTG power technology has been used in spacecrafts such as Voyager 1 and 2, Cassini-Huygens and New Horizons, and in other devices, such as the Mars Science Laboratory, for long-term nuclear power generation.